evaluate the limit. In this case, the only way you can evaluate this limit if you can put this expression in a form for which you can take the limit to infinity. And so this would require that we somehow get rid of this I squared. Ideally, it would be replaced by something in terms of n. So here's what I will do. This can be rewritten as follows. We have a sum of terms which depends on I. Well, yeah, it depends on I, and the value is precisely I squared. So n cubed is really just a factor here. If I divide every term in this sum by n cubed, then I can just sum all terms in this sum and then divide by n cubed. So it's the same thing. I am allowed to do this. I am allowed to take n cubed outside of the limit. I'm sorry, not the limit, the sum. But then what do I do if I, for example, want to take I squared outside of the sum? Well, I cannot, because this sum literally depends on I. And if it depends on I cannot take this I outside. So that is the idea. Now, what can you say about this expression? For this, I don't think there's any way around it. You just need to have seen it before, maybe. It's just like the fact that sum of all elements from 1 to n is equal to n times n plus 1 divided by 2. This is, for example, the Gaussian sum. So this is true because, well, for reasons we don't want to jump into. But for example, for I squared, we also have a formula. It's not this squared, but it is given as follows. So it is n times n plus 1 times 2n plus 2 divided by 6. Now, if you've never seen this before, and I highly recommend this, I think you should stop the video and prove this using induction. If you do this, I don't think you'll ever forget it. So this is very important. Okay, and now with this knowledge, I can rewrite this limit. So I'll call this L. Then by this formula, I have that L is still a limit then tends to infinity of 1 over n cubed on one hand, and this formula on the other hand. And simply, this is a race to see which one goes faster to infinity. Is it the numerator, is it the denominator, or do they go at the same pace? And if this is a degree 3 polynomial downstairs, times 6, of course, it has a coefficient of 6 now. Maybe I'll write it here. So we have 6n cubed. And here we have this expression. Now there are two things you could do. You could expand this whole expression. This is really something you could do, and it's not a bad exercise. Here you have 2 terms, here you have 2 terms and 1. So it will be probably 4 terms. You need to expand 4 terms. You can expand them, write them down. But then we're taking the limit. So if we're taking the limit, then it only matters to look at the fastest growing terms. The reason why I see that this is clearly not going to go to 0 is because what we have above is a degree 3 polynomial. And if you ask me, hey, Omar, how did you see this? This is very unclear. But then I'll just tell you that you have n times 2n. So it's 2n cubed divided by 6n cubed. So the answer is 1/3.